This video outlines the basics of controlling a servo with the Raspberry Pi. You should already be familiar with how to use pulse width modulation to change the brightness of an LED. We'll be looking at the Tower Pro SG90. Exact specifications are hard to come by, so the following numbers may vary. The servo works off of 4.8 volts, though it will still work perfectly fine off of 5 volts. It takes about a tenth of a second for the servo to move 60 degrees, has a maximum torque of approximately 1.6 kilograms centimeters, and weighs only 9 grams. To control the servo, it requires pulses that are high for about 0.5 milliseconds to 2.5 milliseconds. Note that there are 3 wires that lead into the servo, which in this case are for signal, positive, and negative. Unlike a motor, most servos, including the SG90, can't rotate through a complete 360 degrees. Instead, a servo has a neutral position, along with a maximum counterclockwise and clockwise rotation, in this case at 0 and 180 degrees respectively. To set the servo to its neutral position, it needs a high pulse from an output pin for 1.5 milliseconds. To set it to 0 degrees, it needs a high pulse for 0.5 milliseconds. And for 180 degrees, it needs a high pulse for 2.5 milliseconds. Note that these pulse lengths are independent of the current position of the servo. So no matter what angle the servo is at, a high pulse for 1.5 milliseconds will cause the servo to turn towards neutral. This program is simply to demonstrate how the servo can be set to its neutral position. Pin 7 will be used to send pulses to the servo. The pin will go high for 1.5 milliseconds, then there will be a 2-second pause, and the loop will repeat until there is a keyboard interrupt. In this way, we can see what the high pulse does to the servo. So I've got the servo connected with pin 2 attached to positive, pin 6 attached to negative, and pin 7 attached to signal. Let's run the program. Notice that each pulse sends the servo towards the neutral position, but a pulse by itself is insufficient. It doesn't matter where the servo arm begins, it always tends towards neutral during the pulse. So clearly we need to have pulses much more frequently than 1 every 2 seconds. An obvious solution is to use pulse width modulation where we get a pulse which regularly repeats. For instance, pulse width modulation at 50 Hz will send 50 pulses in 1 second, and each pulse will only take 20 milliseconds. Though this presents us with a problem as the pulses are way too long. At a duty cycle of 50%, we see that they are high for 10 milliseconds. As mentioned before, we want pulses that are 0.5, 1.5, and 2.5 milliseconds long, which gives these traces over 20 milliseconds. This gives the following duty cycles. So this means that all we need to do to rotate the servo is change the duty cycle of the output pin connected to the signal pin on the servo. So let's make some alterations to the code. First, let's set pin 7 as a pulse width modulated pin with a frequency of 50 Hz. Then we can start the pulse width modulation with a duty cycle of 7.5, which corresponds to the neutral position. In the loop, I have changed the code to cycle through 3 different cycles. The first corresponds to neutral, the second corresponds to 180 degrees, and the third corresponds to 0 degrees. Lastly, it's good practice to include a statement to stop pulse width modulation when the program ends. Running the program, we see the servo is rotating as expected, but there's something to be careful about. As we are applying pulse width modulation through software, we can run into timing issues. For instance, let's see what happens if we leave the duty cycle at 7.5 milliseconds and only have a print command in the loop. The servo stays close to neutral, but it's going a little crazy. This is important to note if you want a high degree of precision. If you need that, you'll need to use a hardware implementation of pulse width modulation. If you're not worried about precision, then the software implementation should work well enough for servo control.